All right, here we go with Chapter 3, PowerPoints, Gravity and Motion. This picks up pretty much where Chapter 2 left off with Isaac Newton, as we're going to see. We're basically going to go through some different formulas that Newton came up with. This first picture here is, of course, showing one of the old space shuttles being launched into space. Isaac Newton was the first one to figure out how fast something has to go to leave the Earth and never come back. In fact, there's two different motions, two different velocities. One's called the escape velocity. The space shuttle here is not going to reach the escape velocity, and the other is called the orbital velocity, and that's like things that go around the Earth, like different satellites and things like that. The International Space Station, they're traveling at the orbital velocity, and we'll see the difference between the two. The formula is actually very similar. There's only a difference of a square root of 2 in the two formulas. All right, so anyhow, Newton came up with this idea. He was the first one. So going back just a little bit, I'm going to talk about Newton's laws of motion just very briefly, because this is not a physics class. This is just dealing with these ideas in terms of how they help us understand astronomy. So Galileo actually comes up with the idea of inertia, which turns out to be Newton's first law of motion. All right. By the way, these are different than Kepler's laws. Remember, Kepler's laws are the laws of planetary motion. These are just general laws of motion. So inertia basically here, let's look at the picture. Inertia, this is how Galileo figured this out, is that if you disregard friction, all right, so if friction is not taken into account, the ball rolling down this incline would roll up the other incline and reach the same height that it rolled down. And that was actually a pretty profound observation that Galileo made. It it went against Aristotle, of course, because Aristotle, for some reason, gets very fixated on friction, and so this is like if you take away friction, um, then this law is true, and this again, this is a universal law of motion. This is another way to look at the first law. You can have multiple forces acting on an object, but when the forces add up to zero, then there's not going to be any acceleration. All right, that's basically another way of looking at um, Isaac Newton's first law of motion, general law. All right, you know these astronomers in the ancient times, and even right up to Kepler, did not equate gravity with motion in the heavens, astronomical motion. Um, it's kind of funny that people think that Newton or Galileo was the ones to first come up with gravity, but people had thought about gravity for a long time. I mean, it was commonly understood that things fall because of gravity on the Earth. What was extraordinary is to think that there's this force on Earth that extends out into space, and what I generally talk about with this particular thing, you go back to the last chapter, chapter 2, when Galileo was first turning his telescope in the year 1609 to the night sky. One of the observations, and he writes this down and puts it in his famous book, The Starry Messenger. What he does is when he looks at the moon with his primitive telescope, he sees valleys and mountains, and goes even further and describes the moon as as a real place. He even compares the moon with its valleys and mountains to Italian countryside, and I think that kind of influences Isaac Newton to start thinking about gravity in a more universal thought. That you thinking about it in a more universal way. Of course, Galileo applies what became known as the scientific method, coming up with ideas, but then testing those ideas through experimentation. So that when Newton comes along, and of course, he knew that the planets were going around the sun. He was well established as a Copernican, that, anyhow, if the planets and other objects, there's other objects out there besides just the planets, comets, asteroids, there's even what are called minor planets, but they're all orbiting around the sun. And, to do that, there must be a force for them to constantly change directions, right? Because they're moving in these elliptical orbits, some much more elliptical than others, and the only way for them to do that is there must be a force. And even Kepler, going back to his time, he hinted at maybe it was magnetism or something like that, but it turned out to be, of course, gravitation. And you might say, well, how is the gravity the gravity of the sun going to affect everything else in the solar system, right? One of the things to realize is the sun has, like, if you were to add up all the mass of all the other things in the solar system, planets, comets, asteroids, bits of little space rock and so forth, if you were to add all of that mass up, it comes to less than 1%. All right, so I want you to understand this. Less than 1% the mass of the sun. The sun is incredibly massive compared to everything else. And so the sun's mass, which of course is, that's how its gravity is felt, but by the amount of mass that it has, really affects the motion of everything else in the solar system. All right. This is just a little, so, if you were to whirl, for example, a ball around on a string, there's a force, an inward force, that is keeping the ball moving in a circle. And by the way, this is what we call centripetal acceleration. We'll get back to that shortly. But so Isaac Newton comes along and he comes up with this universal law of gravitation, and we're going to get into that. What we mean by universal is, the laws of gravity work just as well here in our solar system, controlling the motion of the planets or the motion of stars in some distant galaxy, right? You add up the mass that's there, and you can tell what these different stars are doing, or even the motion of galaxies themselves is controlled by gravitation. All right, so it is a universal. No matter where you are in the universe, there is this gravitational force that exists between. Well, Newton thought of gravity as a force, and what is this? Let's see. So Newton comes up with this idea of gravity, and it's not until actually Einstein that we come up with a new. Einstein comes up with a new theory of gravity. Just to let you know, the theory, the formula that we're about to see for Isaac Newton, which is more than 350 years old, is still used today. We use it to send spacecraft to the moon or to other planets and things like that. What Einstein does to the theory of gravity is he basically corrects it for really massive objects. And it allows us to start talking about things like black holes, where a massive star has died, a really massive star has died and exploded, and that's a different story. But the theory of general relativity, which is the modern theory of gravity, explains that. And with relatively low mass objects like planets and ordinary stars, Newton's equations work just fine. So here's a thing that Newton discovered, and he even draws pictures of it in his book. If you have a cannon on a mountain and you pack it with some gunpowder, the ball, the cannonball will go a certain distance. If you put more gunpowder, it'll go further. Newton, being the genius that he was, said, "Well, how much, how fast would the ball have to go to continue to keep going around the Earth?" And so that's actually what we call orbital velocity. And Newton was the first one to work out the value for the orbital velocity. All right, so before again, this is more physics than anything. I'm just going to briefly talk about this. If a car is or anything really is traveling in a straight line with the same speed, then there is no acceleration taking place. When a car speeds up or it slows down, by the way, so either one, that's considered acceleration. Another way for something to accelerate is to maintain the same speed, right? Notice 10 miles an hour, but you're going around corners, and anytime something changes direction, it's undergoing acceleration. That's important for the planets. All right, so I want to make sure that everybody understands there's a difference between mass and weight. Mass is a measure of the amount of inertia an object has. Like, for example, if you have a rock on Earth and that rock has a mass of 3 grams, on the moon, that same rock would have a mass of 3 grams. However, its weight would be different, right? The weight is the thing that is different. And that's because of the acceleration due to gravity on the surface of the moon. On the moon, things are about 6 times. So you take whatever the weight is and you divide it by 6. For example, an astronaut that weighs 200 pounds on Earth would weigh, you just divide that by 6. They would feel as though they weigh only 33 pounds. On Mars, it's about 1/4. So this is another way of looking at Newton's second law of motion. If you take an empty cart, a shopping cart, and you give it a certain force, you'll get a large acceleration. If you take the same cart and you fill it with groceries, you give it the same force, it's not going to accelerate as much because there's more mass involved. Sometimes that's called Newton's second. Well, not sometimes. It's called Newton's second law of motion. It's also another way of saying F equals ma. Force is equal to mass times acceleration. His third law, if you were to, for example, push on a wall, and what the wall doesn't give or anything like that, let's say you push with 10 pounds of force. By the way, with standard international units, the units of force are actually called newtons, just to let you know. But if I pushed on the wall with 10 pounds of force, the wall pushes back on me with 10 pounds of force. That's called the third law. This is important a little bit later when in physics, where you start dealing with what's called momentum. All right, so here's the formula for if you had 2 masses, and they don't have to be the same mass, and their centers are a distance d apart. This is what's called an inverse square law. Now, Newton's the one who comes up with this. It says the force of gravity between these 2 objects is equal to a constant times the product of the 2 masses. The masses have to be in kilograms, and the distance between their centers squared. Now, the distance has to be in units of meters, and big G, capital G, is the universal gravitational constant. You'll get to know that number very, very well. We'll do some examples, and then of course F is the force, and the force is usually measured in newtons. as I mentioned before. All right, let's. I'm going to go on with the next video. I'll pick up this